Can you see this Mathematica screen?
Yes, sir. You can see.
Okay, so I will just show you
Yes, sir.
by, I'll start by just showing you some of the things we discussed earlier, that if I have a wave function, how should I plot it? So, of course, you probably already know these, those who have played a little bit. So, let's say I want to plot the 1D particle in a box, and this I want to write it as this, and where let's say L is equal to 10. Okay, so N also needs to be written. Oops, L is 10 means, okay. So this is what we expected. So N equal to 2 will have 2 nodes, N equal to 3 will have 3 nodes, and so on. Okay, that's a straightforward thing. Now let's do it for particle in a box, in a 2D box. So that is what I wanted to show you the symmetry. So what it will be? It will be n pi x times m pi x. Okay. So let's say m is also we have to define. So let's say first we'll plot the ground state. So this is a 3D plot, and this goes from. So this is how it looks like. This is what I told you last time, that it is like a particle in a box one direction, and the other direction is flat because the wave function has to vanish at the boundary anyways. Okay. So okay, so there is something a bit of n pi x by L. Was that the wave function? Can somebody check that is the wave function?
So it's m pi y, no?
Oh yeah,
By
yeah,
Y.
that's what I, yeah, because it has to vanish at both boundaries, right? It is not vanishing. So definitely I have done something wrong, and this is the error I made. Okay, it must vanish in both boundaries. Okay, makes sense. Okay, now let's do next one. So next one will have one node. It's now notice it's not a nodal point, it's a nodal line now, because it's product of a node in one direction and no node in other direction. So when you multiply them, this is how it looks like. And you can now keep plotting more and more complicated wave function, of course. More and more nodes you have. Okay, this kind of nodes you will have. Now, if you remember earlier, I talked about that 1, 2, and 2, 1 are basically partners. Okay, so actually, it is best seen if I do a contour plot. So let me do a contour plot. Contour plot. If I do this contour plot, this peak and the crest is represented by some color, okay, instead of showing this 3D projection. So this is how it will look like. Oh, why it is taking so long to run? Yeah, so this is how it look like. So if it is a peak, it is a bright yellow color, and if it is a crest, it's a bright blue color. So did everybody follow that? What is a contour plot?
Yes, sir.
Okay, so 1, 1 has only one peak at the center. Okay, so 1, 2 has one peak in one side and one crest in the other side. Now, what will happen? So now I told you earlier that 1, 2, and 2, 1 are degenerate. So degenerate means they have the same energy but two different wave function. So can somebody predict that what is going to happen for 2, 1? So remember 1, 2, and 2, 1 are degenerate because of the symmetry of the Hamiltonian, and the symmetry is if I flip a square, then it's still x square. Okay, flip means flip 90 degree. Okay? So that means 2, 1 will be a 90-degree flip partner, which is this. Okay, everybody follows?
Yes, sir.
Okay, now this middle line is a nodal line. So number of nodal line will increase if I plot more and more complicated wave function. So let me plot 2, 2. Can you hear me? I got disconnected for a moment.
Yes, sir. We can hear you now.
Yes, sir.
And
Now.
see the screen also, right?
Yes, sir.
Okay. So 2 2 was this, and as I said, that 3 2 is this. So 2 3 will be again 90-degree flip partner. Okay, like that, and so on. So you can even plot like anything, 7 8. It will be just more and more nodal points. More and more nodal points will appear, right? So this is basically how you can plot any generic wave function and understand this kind of symmetry. Now what if again, as I said, that for square lattice it is not there. Did somebody check that sum of squares of two different pairs of number, can they be same other than flipping them? Which means if I say n is equal to a square plus b square, you can also say it's a Pythagorean partner set. A square, no, not necessarily Pythagorean. It needs not be Pythagorean because the other side need not be a square. Okay, but is that unique? That is my question. Okay, I didn't check that. I didn't get time to. So why don't you check that? Then you will know if there is a degeneracy or not. So okay. So let's come back to the usual topic. My other screen is probably not visible. So let me make the other screen visible.
Sir,
Yes.
sir, 50, if we take the number, then like it can be expressed as 7 and okay, nothing. Leave it.
Yeah. So I was my question was this, that if I take an integer which can be expressed, let's say an integer that can be expressed as a sum of squares, okay, then is this sum unique? Which means if I do b square plus a square, then it is not unique, the same thing. But
Sir, if you are taking 50, then it can be sum of 7 square plus 1 square as well as 5 square plus 5 square.
fantastic, very good. So that means at least one exception is there. Therefore, exception means one example is there. Then therefore there must be many examples. Okay. So you can imagine the wave function which is 5 5. That is its own symmetric partner, right? 5 5 is 5 5, but 1 7 and 7 1. So how will this wave function look like? This wave function will look like there will be 5 such nodes, right? There will be 5 such nodes, up down up down. And then 7 1 will look like there is 7 node in one direction but only one in other direction, and so on. Actually none in other direction. Okay? So similarly this one 1 7 will look like this, 7 in one direction, right? Are you getting what I am plotting?
Yes, sir.
Okay, so that means, and they are not related. Okay, so if you flip this you get one from another, but there is no connection between these. Okay, so this is what is an example of an accidental degeneracy. And so now let's go over and understand that what kind of scenario can give you degeneracy and when you don't have this degeneracy. For example, okay, let me plot this also. So let's plot this. So 1 7, actually let me plot it, three of them side by side. So this is 1 7, 7 1 and 5 5. 7 1 5 5. So you can see one of them as I have drawn by hand. One of them has 7 high peaks and crest in one direction. 1 7 and 7 1 are related. You can just flip one to get other, but 5 5 is totally different. There is no continuous connection between these ones. Okay. So this is a nice example, and there are many such examples for this kind. So you have to go a little higher. You won't get it in 1 2 2 3 level. Okay. Very good. Okay, so what else do I need to show anything in the plots? Let's check once. Okay, no, probably I can now switch to. Okay, one more thing I want to show. So what if the this thing is a rectangular well? Okay, so rectangular well means I have Lx and Ly. Okay? So that means there is that symmetry is immediately broken. So let's say I have let me define a Lx equal to 10 and Ly equal to 15. So then this means Lx. So let me plot something simple. So 1 and 2. Okay, now I've broken the asymmetry. Okay. So now I can also plot the other way, which means 1 and 2 and 1. Now this is not a flip partner. You cannot just flip one and get the other picture, because now it is rectangle. The LX-LY symmetry is broken. So NX and NY need not be, even if they are per pair, the wave function is not going to match. Okay? The Hamiltonian doesn't have the symmetry, wave function doesn't have the symmetry either. Okay, so this is what I wanted to show you from mathematical. Now I will switch to writing. Okay, I have to share the screen again. This is why sometimes online classes are nice, because this kind of arrangements are very complicated to make. Once you switch and do this, then half the class goes in that. Okay, so now let's come back to the usual way, and let me remind you that what we are doing, that we were studying this particle in infinite well. And we found that the wave function, so this is infinity outside and 0 inside, and we found that the wave function will be of the form psi xy root 2 and 2. If you write like that too for better remembering. Okay, this was the function, and we said that there is a degeneracy when you just label a state with this pair of numbers and you exchange in x and ny. Plus also there is another degeneracy. So this is one kind of degeneracy. One is exchange in x and y, and another one, as you pointed out, is of this form. Okay. This is the accidental degeneracy. Actually, these accidental degeneracies also have some, sometimes, not always, have some deeper symmetry, which is not obviously visible. But in this case, there is none. But sometimes you can have something which you cannot find easily. It can be, but it's not easy to prove. Yeah. But one thing is definitely true, that symmetry corresponds to degeneracy. So this is, we will dwell on this particular point later. And because we have already learned in classical mechanics that symmetry implies conserved quantity, but here I'm saying symmetry implies degeneracy. We'll see these statements are connected. So then let's talk about the types of degeneracy. In this problem for particle in a 2D well, and you can also extend this in a higher dimensional well. The first one is symmetry related, which comes because Lx equal to Ly. if it is a square well, not rectangular. Now the second one comes if it is rectangular but rational. Okay. So then it's an accidental symmetry. Or hidden symmetry. So you can see that what you have to do, you have to find a pair of integer such that these two things are equal, right? So nx square by lx square is equal to ny square by ly square, which means you have to any pair you take, which is lx by ly square is ny by nx square. So if this is given to you, so ny by nx you have to choose, and they are not going to be any symmetric partners. So when you choose them, then you will find them to be actually you will find them symmetric partner. Yeah. So you will find them it is equivalent to flipping, but then these are more restricted choice. There are very few, much more fewer such choices. Now there is another kind of symmetry you will find, which is lx plus ly square is rational, but lx by ly is irrational. So this is not accidental. So check this, that how they look like. Now it can happen that Lx by Ly is irrational. So let's say Lx by Ly you have chosen such that it is root 2, but the square is 2, so the square is rational. Okay? Or any such weird combination you can say, think of root 3 by 5 and the square is 3 by 5. And as you can see, it is the square that determines the degeneracy, not the ratio itself. But if you have the ratio irrational, then you will find there is no way to connect these two things by a rotation or anything. So this is an example of a accidental degeneracy. And then it can happen that your Lx by Ly square itself is, you set that to be degeneracy. Sorry, it set that to be irrational. Then there is no degeneracy. Of course, because then you cannot find such a pair of integer whose square is going to be irrational. So these are all the possibilities. This irrational point is actually very important. This fact that you can destroy symmetries by choosing a irrational number as a length. Of course, physically you can ask what does it actually mean, because you may not get it. So that can be also discussed. So in real world problem, there is something. How do you actually make something irrational? But it turns out that you can do that, and when you can do that, it leads to very interesting physics. So one of your senior have done fantastic work on it with me, and Parvati. So you can ask her that what happens when there is the irrational number in the problem. But we will not go into that. But just know that irrational number can destroy symmetries, and if symmetries are destroyed, then new kind of physics emerges. So I will not go far details into that, because the full analysis of this will require group theory, and probably given your current mathematical background, it may not be easy to do. So but just know that this kind of classification exists. So now let's go on to talk about a particle in the 3D box. The 3D box means I have a 3D box which is infinite outside. Everything is infinite outside. So then you can easily extend these ideas, and you can get the wave function to be the energy levels to be I h bar square by 2m and the wave function will be you can also plot these things, but it's a little more difficult to visualize. There are these 3D contour plots also. Okay. Okay, everybody is clear of the full story of particle in a box?
Yes, sir.
Okay, how about someone else?
Yes, sir.
Okay, so now let's move to particle in a 2D harmonic oscillator. Okay. I hope you all understand that everything is far, far easier than first half of the quantum mechanics course. This is what I have been talking about for a long time. Okay, there is one more thing, one more interesting thing, which, okay, so I will just give you a hint and I will ask you to think about this. So let's say that you have a particle in a box problem, okay? So I can always give you, so particle in a box problem means these are the eigenstate. So think about these sort of problems and I want you to try as exercise that I can always give you the particle in a state like that. So let's say what 2 by root 7 is psi 3x. So let me call it some phi tilde psi tilde x. Okay, I don't need the tilde if I'm using it. So phi 3 is the third eigenstate. Just like we have done earlier, right? You can have a arbitrary state, which is some Cn an of some operator or En, the eigen operator, the high Hamiltonian operator. So this is a similar spirit. So all I'm doing is I'm just putting the x in this side and putting the x in this side as well. So this is nothing but phi. This is nothing but this. So let's say I choose this to be this plus 5x. So if it is 2 by 7, what it will be? 4 plus root 3 by 7. So let's say I can prepare a wave function like this, right? And I ask you the question. This is something we already discussed. So now I ask you the question. If it is your wave function at time 0, what will be at time t? So try this. I already pointed out this kind of exercises also in the assignment pages, but try this. And then I want you to think about this problem. So sketch this, draw this wave function in Mathematica. So let's say I have a particle in a 2D box. And the wave function, so I am writing this in a little cryptic way because I have to write a long expression otherwise, is in a superposition state, 1, 5 plus 5, 1. Okay, this superposition state. So you have to write the wave function actually with proper normalization constant, of course. Some prefactor and proper normalization. Okay? Or you could be in the state 1, 5 plus 2, 7. Or it could be one of your symmetric pair of state. So you can now, if it is in a superposition, if you sketch the wave function, then it might be hard to see any symmetry because now it is two defined symmetry form, and look at that how this wave function actually looks like. So you can show that you can see that there will be two classes of example when you do this exercise, and some of them are separable, and separable means you can clearly make out the positive negative part, and some of them are not separable. So they are in a very strange way when mixed up. So this will lead a way towards studying entanglement in particle in a box kind of problem. So again, entanglement something you'll learn in quantum mechanics too. That's why I'm not talking about it. But anyway, for now, do this exercise that you should be at least familiar with this kind of problems. That if I give you an arbitrary state, a superposition state, how to calculate the dynamics, and if I give you similar thing in 2D or 3D, how to calculate the dynamics and calculate any expectation value. Okay. So everybody knows this part, right? If I give you this state that okay, I can see that there is a delay. Can you hear me clearly?
Yes, sir.
I'm writing something, you cannot see that. Or okay, now it came. Okay. Yeah, so everybody knows this exercise, right? If I give you a psi x0, you know how to calculate the psi xt. This is something we discussed extensively in class. Okay, study this because you have a quiz coming on Wednesday, which is on dynamics. Okay, so if you have not, this is very surprising. That means you are not even one person in the whole class is following the class in real speed, which means you are all lagging. Where, who knows? Okay, so let's do the particle in a 2D simple harmonic oscillator. I cannot, of course, keep revising old stuff. Then we'll never finish any syllabus. So let's move on. Okay. So particle in a 2D harmonic oscillator means you have a potential which is of this form. Now this is a separable potential. This is Bs plus By. So therefore, I should be able to play the same game. And it turns out that if I do this, so then this form is the same principle, same idea, but of course I am not going to repeat the harmonic oscillator series solution and whatnot. You have to do this solution and by separation of variable, and it's just, even intuitively you know if separation of variable is allowed, then it is nothing but the sum of the energies of these two oscillators and product, and the wave function is product. Okay? So this is what we have seen already. So E should be total, E should be E n x plus E n y. This is something I briefly mentioned last time. So this is n x plus n y. And so on, and the phi xy will be phi x phi y. Okay. There should be n x and y, so phi n x phi. So that means it will be some constant times the Hermite polynomial. So I will do a little bit of as you know that we have this dimensionless parameters to express everything. So let me write down the phi n x is n x and the zeta is nothing but and then actually use a different function. And just writing the solution of two one dimensional oscillator using just different function. So this thing will be times to the power minus zeta square plus zeta square divided by 2. Okay. Now again you can check that you can very easily see that there will be similar form of degeneracy, because now your E is E n x n y is nx plus ny plus 1 times h cut omega. So therefore the degeneracy will be 0 0. So 0 0 is non-degenerate. There will be similar partners 1 0 0 1, and you will start seeing these unrelated partners or accidental degeneracy at as low as 2 0. Okay? Earlier you had to go to this 7 1 5 5. Now here is an example of this. Okay? So this is what I told earlier. This is the problem of partitions. Again, I have, as I said, many vowels means I'll invariably make a mistake in spelling. I don't know how people do these spelling competitions. It requires tremendous amount of memory. So and so on. So you can show that. So partition means if you have given an integer, how many different ways are there, you can express it as a sum of two integers, and that will give you number of degeneracy. And you can show that this is a something you can prove that in this case the degeneracy of nth level is n plus 1. This comes from this partition properties. Now let me tell a little bit. It might appear to be it looks like it's a bit dry to continuously tell, okay, this problem, this potential, this problem, this potential. But now that we have reached here, let me tell just 2 minutes on a fascinating problem which is related to this 2D harmonic oscillator, and that have been the subject matter of 2 Nobel Prizes. So the problem was following. So let's say I have an electron moving in a 2D plane, pure 2D. And how do you make such 2D plane is very difficult. It turns out that you can make this as an interface of two 3D systems, which is somehow insulator, but this interface is carries transport charges. So then it is a perfect 2D. It's a sandwich object. So they are usually, I think, made for indium arsenide, gallium arsenide, something like that. So this was an experiment which Klaus von Klitzing was doing in 1980s, and his agenda was to find some precise measurement, some 2D measurement, and more like that was, I think that was his agenda, was to do some 2D measurement of current voltage in this kind of system. So what he did, he turned on a strong magnetic field, and not very strong, somewhat strong magnetic field in B direction, and they were measuring this using this. So any of you did this Hall experiment, Hall geometry, Hall current?
It is in 7th semester.
Oh, it is there in 7th semester. Okay. So Hall geometry is something like this. This is not a perfect 2D. It looks like this. Okay. So here you apply some, you pass some current, and you apply some voltage drop across this and across this, both direction. Okay. So here also you apply, measure that. So one of them is called transverse resistance. Another is XX, means the longitudinal, and another is the transverse. So what he found, as he tunes the magnetic field, this resistance goes like this. And the other one, what I don't remember what the transverse and this one of them does that, another of them does that. So let's focus on only this one. Okay. So some R and versus B. So this is very strange, because you know that resistance of a material generally is a linear function of temperature or something else. Of course, one cannot say easily what will happen with magnetic field, but something is not growing straight but going like a step. So then he checked this, he performed this experiment in different material. He reported that it became a famous result. It turns out that at which value of R this appears, that is independent of a system, independent of, so people replicated this result across different labs in the world, different material, different system, and found these plateaus appear always at n e square by h. Okay? This number. Now E is a fundamental constant, it's charge of electron. H bar is a Planck constant. So it's a fundamental constant times n. So that is fascinating. So resistance of a material shows a property which is universal, which is nothing to do with the material. It is true for any material across the world of this kind. Okay. So then this was a big subject, and in 1984, I think he was given Nobel Prize for that. And then in another phenomena came out few years later, where people increased the magnetic field to be much stronger. Okay? Few means actually 98, that second Nobel Prize was given on that. And and these plateaus appear somewhere in between also, some fractional number. So this n is an integer in this case. This phenomena is called quantum Hall effect, and n is fraction for fractional quantum Hall effect. Now, why I am talking about this problem in this context? Because you can show the problem of electron in a magnetic field. This is what we will learn in first 2 weeks in quantum mechanics 2. Problem of electron in a magnetic field, in a free electron in magnetic field, can be mapped to a problem of 2D harmonic oscillator. Now, if you look at these 2D harmonic oscillators, you will see that these energy levels are constant. Why? Because they are always at the gap. They are always at this gap of h bar omega. Right? So this difference is constant, and they have certain degeneracy. So if I plot them, these energy levels of 2D harmonic oscillator, you will find these, and okay, I have already plotted them. You will find this is your En. You will find this, and then 2 lines and 3 lines and so on. Okay? So this thing, so what it turns out, the where you find those lines, that can be understood from where you find these plateaus. And this is a topological phenomena in the sense that it doesn't depend on the details of your Hamiltonian. So as I told you earlier briefly, the topology means that it's some global property like a genus number of a, that's what tells you a coffee cup is same as donut, but football is not same as coffee cup. So because they have one has one hole, another doesn't have any hole. So this integer is like a topological characterization of the underlying Hilbert space and so on, like the wave function characteristic. And this fraction is actually a many body effect. It is because of when you make the magnetic field too strong, then what happens? So usually the electrons have some kinetic energy and the potential energy. The potential energy is the Coulomb interaction. Now what happens when you make the magnetic field too strong? What happens to electron in a magnetic field? It traverses in a loop, right, along the magnetic field. The loop radius starts getting shrinking, very, very small. And the electron has very less kinetic energy. So then what happens? Its potential energy becomes stronger. The Coulomb interaction energy becomes stronger than the potential energy. Then the whole electron in that system behaves like an interacting liquid. This is called quantum Hall liquid. And this many body state manifests as a fractional number, as if the electron is a fractionalized object. This is a fascinating phenomenon and subject matter of a lot of research today, that how can electron act like a fractionalized object. And I just wanted to tell you the story to tell you how this having a strong grip of this kind of problem can help you navigate to this kind of problem. So take what you are learning now very seriously. They are connected to very fascinating phenomena. Okay, so let's move on, and so let's talk about 2D harmonic oscillator. Continue to talk about 2D harmonic oscillator. So now that you have noticed, this oscillator has some symmetry. Okay, this is X, Y, and Z. And this has some symmetry. And so this is one more thing I wanted to add here. So this phenomena, so this is some of you are interested in mathematics, and also I also like mathematics, but what I particularly like is mathematics seen in real world. Okay, so this is an example of that. So as I told you that this is a donut, right? This donut has one hole, right? But a sphere, a solid sphere doesn't have any hole. So they are different genus number. This is genus number 1, this is genus number 0, those who did some topology earlier. So they are not continuously connected. So this is a similar thing. This integer represents something like genus number of the problem. Of the what problem you then, that is actually something called Berry curvature, which you learn in next semester, that is related to this conductivity of this system. This is also very fascinating, that the wave function phase somehow controls the transport, the conductivity of electron. So, and this Berry curvature has this kind of topological structure which shows up in the resistance. So that means if it has a hole or not, that shows up. And that's why when you go from one material to another material, unless the difference is so high, that it pinches a hole, you won't see any difference. So the microscopic details, that is what the essence of topology, right? Any continuous deformation that doesn't close the hole will keep the system in the same homotopy class. So that is what is happening in this class of system, and therefore it doesn't matter which Hamiltonian, which material you are using. And this is actually used as a unit of resistance now. This is called 1 Klitzing resistance, named after Klitzing. Because as I told you earlier, that unit of resistance should be something that doesn't depend on material or system and location and all those things. This is universal. Okay? This is universal physics. Okay. So,
Okay, I found this
oops,
on the web for his.
oops, my Siri got activated. Okay. So now I will like to demonstrate that how this problem actually can be handled in a much easier. Actually, this is not Z, this is just Vxy, which I can call Z. Okay. So now notice this problem has a symmetry, as I told you earlier, and the symmetry is cylindrical symmetry. So you all know that, let's say if a problem has a circular symmetry, spherical symmetry, cylindrical symmetry, if you solve it in Cartesian coordinate, then the symmetry is not manifested. You cannot see the coordinate system doesn't possess that symmetry, and therefore the problem becomes incredibly hard. So it is much more wise to switch in a polar coordinate or cylindrical coordinate for this problem. Then the symmetries are manifested. So that's what we will do. So I will take a coordinate which is rho xy and phi is tan inverse y by x. So V is then half omega square. Look, this already looks very simple. So half omega square rho square. So this is your potential now. And now you can show that these two cases. So let's say the potential is having symmetrical symmetry. So now if I look at the wave function, so let's say I take psi 1 0 and psi 0 1. So they have this, they don't have this symmetry, right? One of them looks like yeah, you can see it by plotting it. So I'm not just plotting it right now. And so they will have a, so 1 0 will be given by h0x h1y with some normalization. I'm not writing. No, this is 1 and 0. So I am writing this in an approximate form. So let me put a proportional sign. You can just note the full form just from this formula. Just from this formula. I'm just not writing all these complicated expressions. So this will be the form. And since h naught x is 1 and h1x is 2x, so therefore these two are not symmetric forms. Okay? But if I go to this coordinate, which means I take the xy and convert it to rho and phi, then I can write it in this. So okay, there is another thing I have to be careful about. It is not xy, it is, if I look at here, it is eta and zeta. Okay, I want to work with this dimension free quantity. So where I should write eta and zeta. This is eta and zeta. Eta square plus zeta square. Eta square plus zeta square. This is the dimension free quantity. So h0x is generally 1, h1x 2x. So h1 eta and h0 eta will behave accordingly. So now, so check this exercise. So if I go into this coordinate, then it will look like this: n times 2 zeta to the power minus eta square plus eta square by 2, and psi 0 1 will look like Okay, so this is, I'm just, because h naught is 1 and h1 is 2 xi, and vice versa. So this is what the wave function look like, and this doesn't have the symmetry, because as you can see, one is zeta multiplied by Gaussian, another is eta multiplied by Gaussian. But now if I go to the cylindrical coordinate, okay, now it is still not cylindrical. So now if I go to cylindrical coordinate, I can write this wave function as in this form: I10 plus I psi 01. Remember, it is degenerate, so any linear combination is also a legal wave function. So I can always choose a basis which is plus minus like that, and this will become normalization times E phi plus I s phi rho square by 2, which means it will become n2 rho e to the power plus minus I phi e to the power minus rho square by 2. So if I write this two wave function in the cylindrical coordinate, I can take this form. Now notice this is manifestly symmetric. You can clearly see that this is a symmetric wave function. Only you have, the only difference comes from a complex a complex phase factor, which doesn't manifest in the probability. Okay? So therefore, the symmetry of the wave function is manifested when I go to the polar coordinate or the cylindrical coordinate. Okay. So this is what I wanted to show. If you choose the appropriate coordinate that is in symmetry with the system symmetry, then you can manifest the symmetry of the wave function. Okay. Now let me find another quantity. This is called angular momentum. Why am I doing such a thing? So right now I'm doing it this because I know this system has a spherical, has a circular symmetry. Okay. So we know if there is a circular symmetry, there is a conserved quantity which is an angular momentum, and that angular momentum, we know this from classical physics, and we know if an operator exists in classical physics, I can find its quantum counterpart by putting a hat on all the variables. So I am finding that variable. We know that. Why I care about this? Because in this problem, I know that there is a circular symmetry, which means there must be a conserved quantity. So that quantity is xty minus ypx. This is my angular momentum. I put hat on them, then it becomes an operator. Again, I can go to the polar coordinate and it looks like this. Now convince yourself, take this wave function, which I just wrote down here, and show that this is plus minus h bar phi plus minus, which means this wave function is an eigenfunction of Lz. This is not surprising. Why? Because I know, okay, this is something I will show you much more rigorously later, but I know that in this problem from classical mechanics, Lz is generator of rotation, of this rotational symmetry which is there. Lz is generator of rotation. Therefore, Lz, the commutator of Lz with the with this Hamiltonian that has this symmetry must be having vanishing Poisson bracket. If it has a vanishing Poisson bracket, its quantum commutator will be also 0. If quantum commutator is 0, then the two wave functions, then the wave function of h and a, so this is the statement. Lz must be satisfying this, which I know because Lzh must be 0, because I know this because del Lz del t is Lz0, Lzh. Now I know Noether's theorem. This is conserved quantity, therefore this is 0. If this is 0, then this is 0, because this is nothing but 1 by IH part this. And if this is true, then Lz and H must have simultaneous eigengate. I will do these things much more formally later, but let's just say what is my line of thinking, that why did I thought of a Lz and why did I try to check this, that what is the Lz wave function. So now you can show it much more formally as a differential equation. you can see Lz phi. So let's say you want to generally find the solution of Lz without knowing anything about it, without knowing that whether it's a simultaneous eigengate or whatever. So let's say I want to find the eigen solution of this, and this is nothing but minus I h bar del del phi, capital phi, Lz capital phi. And we know that this is just a first order differential equation, and solution must be of the form Lz phi h bar. Okay. And we know that phi must satisfy the constant since this is an angle. What is this? This thing is an angle, angular coordinate. So therefore, it must satisfy. Okay, and this will be only satisfied if Lz equal to mh bar. Why this? Because this tells you e to the power I Lz phi by h bar phi. Okay, let me write it more clearly. So this tells you e to the power I by h bar I plus 2 pi is equal to. Now that means I can multiply there an arbitrary m, actually 2 pi m, because any 2 pi number of rotation will give me the same thing. That just means I Lz pi m by h bar is equal to 1. And that means your Lz, what did I do here? Yeah, so Lz, that means Lz 2 pi m by h bar must be equal to 2 pi. So basically a better way to write this is this. Leave the m and write this as 2 pi m. So this must be equal to 2 pi m, and that means Lz must be equal to mh bar. So Lz must be an integer multiple of h bar. So psi plus minus tells you it is nothing but plus minus h bar. So psi 10 and 0. So this thing is called angular momentum quantum number. This is the eigenvalue of the angular momentum operator. Okay. So this is something from where I will pick up next time. And when this happens, so when you have an angular variable defined on a angular on a with some periodic boundary condition, this thing is called periodic boundary condition, because after 2 pi it is returning to itself. This thing is called a compact variable. So when you compactify one direction, then you get a that corresponding quantum number to be quantified. Quantified means it is integer. Now notice that this we have earlier seen that discretization is because of boundary condition, and boundary condition was what? In particular in a box, we said the wave function must vanish here and here. So this gave me the discrete levels, the discrete wave function. Here I am saying the wave functions must match at this. So this is a circle given by this angle phi, and it says as phi 0 and phi 2 pi it must match. So this thing is called compactification, compactifying the dimension, and that gives me discretization. So I will end this class with one one problem for you to try, and that is another very interesting problem. That problem is think of a one-dimensional particle on a ring. Okay, one particle moving on a ring. Okay, so calculate the energy eigenvalues and calculate the this Lz operator eigenvalues also. This problem is particularly fascinating because you will see that if you turn on a magnetic field at the center, and the magnetic field is only here, so that means the particle cannot experience the magnetic field. It's a solenoid. Let's say it's an infinite solenoid. This is something we'll first you do this problem. This is an interesting problem just to do for this semester. This is for next semester. If I put a solenoid, that means the magnetic field is strictly confined here. It doesn't go anywhere outside. Okay. So this is something I'm telling you, something little interesting. It is not necessary for this course. It's those who are interested, so it's for them. So if I put it in a solenoid, the magnetic field exists only inside the solenoid. Okay. So that means there is no magnetic field outside. So the particle doesn't see any magnetic field. So now you can see the energy levels of this system changes when you turn on the magnetic field versus when you, so let's say there is no magnetic field initially, then you turn on the solenoid, then you turn on a magnetic field, then the energy level and wave function changes. So this phenomena tells you that a particle doesn't experience the magnetic field, but so you can show this. And did you do this exercise in classical mechanics? If I have an infinite solenoid, not classical mechanics, electrodynamics, calculate the magnetic field, calculate the vector potential, all those things. Did you do that sort of problem? Is anybody there?
Yes, sir, we have not done, but we will.
Okay, so then I think there is not much point talking about it. This problem, when you do that, it's a Griffiths example. You'll see the magnetic field is non-zero inside, but it's zero outside, and but the vector potential is non-zero outside. The vector potential A. So you will see that even if the particle is not experiencing a magnetic field, but only experiencing the vector potential, its energy level will change, and that change is detectable in experiment. This was done in experiment. Now this has a very far-reaching consequence in our understanding of physics, because what did we understand? We thought the real thing is field and force, and potential is a fictitious quantity that helps us to calculate field and force. But this example will show you that the real deal is potential, because the particle is at a place where it is not experiencing any magnetic field, only experiencing the potential, and that is enough to change its energy eigenvalue and and everything that is measurable. Okay. So this is something we'll learn in next semester, something called Arnold-Bohm phase and all. One can do an interference experiment also with that. Okay, that's all. That's all from my side for today.
Thank you.